Um, all right, our topic now, we're moving on from our primary focus original has been so far on discrete random variables to what are known as continuous random variables. And this is where there is all of the main concepts remain the same. However, there is some important there are some technical aspects that come into play here, and in particular, this is where calculus starts to make its way into into the course. So it's really for those who, well, it is possible in some way to understand this material without calculus, but at some level, but not really if you want to understand it fully. So this is where we're going to be talking about introducing calculus into the course. So okay, so what is the we've run through some examples before earlier, much earlier in the course of where um of what a continuous random variable or a continuous probability distribution will be. And remember what the example was at that time for a continuous probability model. Was we had imagined a disk of unit circumference which has a spinner or some kind of arrow attached from the center. So we have a needle. And we want to measure the arc length from X, the arc length, we'll call it X, from the origin point. And we'll write the origin as O. So the origin point is here. This arc length is going to be here. Okay, so we can consider the sample space. In this case, it's a unit circumference disk. So the arc length will be anything from 0 to 1. We include 0, we exclude 1. So we have to make a decision on that endpoint, because when the spinner comes and loops back around, if it were to land perfectly on that horizontal, we would have to make a decision. It is both one full revolution around, but also 0 length. So we would count that as a 0. For finitely many subintervals, so we'll write them as, so we assume they're non-overlapping. J1 up through Jn. We will define the probability measure on this, the probability of the disjoint union of these subintervals as the sum of the arc lengths of those subintervals. And in particular, probability of omega. Well, what is omega? By definition, up here we've defined omega as the unit interval. What is the length of the unit interval? It's 1 minus 0. And so the probability of omega is 1, as it needs to be. What's the probability of finishing in the top half sphere, top half of the circle? Well, it's probability 1/2 minus 0. Again, it's 1/2. And that's also equal to the same as the probability of landing in the bottom from 1/2 to 1. Notice that the inclusion or exclusion of endpoints doesn't actually matter in this. And finally, let's look at what's the probability of landing at any particular point on the circle. Well, the point X is the closed interval, can be thought of as the closed interval from X to X. What is the length of the closed interval? The length of the closed interval is X minus X, which is 0. Okay, so this is something that we're going to notice in conditional or in continuous random variables that we did not see in discrete random variables, which is that the importance of countable additivity in our definition of the probability axioms. So what I mean by that is, think about how we are spinning this needle, and it comes and it lands at a specific point, let's say here. And so theoretically, we say there is some measurement, some precise measurement between 0 and 1, and that is the point. And it's any real number between 0 and 1 where it could land. But for all practical purposes, we will never be able to measure precisely the exact point. And the probability ahead of time of saying it's going to hit exactly this particular point where we identify a specific point is 0. So the probability of occurring at any given point is 0, but we do have countable additivity of P, meaning that we can decompose omega into a countable disjoint union, but we cannot say, so this is technically, we could write omega as the union over all singleton omegas. Okay, but note and be very clear that this is not, we cannot calculate this by summing over the probabilities of the individual pieces, because the individual pieces each have probability 1, that would be 0. But this is not a contradiction. Why is this not a contradiction? Because this is an uncountable union. Okay, so is uncountable. So we don't have uncountable additivity in probability. Okay, and so that's the biggest difference. And it does have some significant ramifications and a significant impact when we try to formalize this, as we'll see.